I hope everyone can see my screen. Can everyone see my screen?
Yes, ma'am. It's visible.
Okay,
Yes, ma'am.
okay, thank you.
Yes, ma'am.
Okay, okay, thank you. Before we begin the, before we continue with the applications, just remember that this is Gauss's law, okay? Integration E dot n cap ds equal to q by epsilon naught, where E is the electric field that we need to find out, n cap is the normal to the surface at a particular point with infinitesimal area ds, and we need to find this surface integral, and that is equal to q by epsilon naught, where q is the total charge that is enclosed by the surface. And if you remember the steps, for example, if we go to this field due to a point charge, this is just for your recapitulation because this was a new thing that we did in our last class. So if you remember the steps, then this is the point charge, and first we determine the symmetry of the problem. Okay, so we know that for a point charge, all the field lines, the electric lines of force, are radially outwards, so they are all in the radial direction, right? So the symmetry of this problem is spherical. So what do we do? Next step, we draw our imaginary surface, that is the Gaussian surface. Okay, and in this case we draw a spherical surface with the charge at its center. At the spherical surface that we draw, that is the Gaussian that we draw, is passing through the point P at which we want to find out the electric field. Okay, so the radius of this spherical Gaussian surface is r, that is the distance from the charge q at which we want to find out the field. So now we apply Gauss's law. Okay, so first we have to find out E dot n cap ds. Now here n cap is along r cap because the surface is spherical. So at any point the normal will be along the radius. So n cap is equal to r cap. Also the electric field we know at any point is directed radially outwards, because for a point charge all the field lines will be directed radially outwards. So we can write E as a function of r into r cap. So E is also along r cap. So in the equation E dot n cap ds, we can write inside the integration E r cap dot r cap ds. So r cap dot r cap is 1. So we are left with E integration ds equal to q by epsilon naught. Now integration ds means ds is an infinitesimal surface on this imaginary sphere that we drew. So integration ds would mean the total surface area of that sphere. And for a sphere of radius r, we know that the total surface area is 4 pi r square. So now here we can write E into 4 pi r square equal to q by epsilon naught. So finally we get the electric field E equal to q by 4 pi epsilon naught r square. Okay, this was for the sphere. Then for the cylinder, what did we do? The problem says we are trying to find the field due to an infinite line of charge, meaning that it is a very long wire or maybe thread or stick which has a charge distribution on it. And since the diameter of this wire or thread or stick, whatever we are talking about, is very small compared to its length, we can imagine that it is very, very long, so long that we call it infinitely long. Of course, you cannot practically have a wire that is infinitely long, but if its length is very, very large compared to its diameter, then we, in mathematical terms, we say that it is infinitely long. Now again, so the information given is that radius of the charge carrying line is A and the uniform charge density in it is lambda. Now this is linear charge density because we are considering a line charge. Okay. Now first you have to again determine the symmetry of the problem. Now if you take any point on this line, you can see that the lines of force will be going out in all directions like this on a circular plane. On another point you will have lines of force like this, on another point like this. So all along this line charge distribution, at every point you have lines of force which are going out in this manner, assuming that the charges are positive. So we can say that this problem has a cylindrical symmetry. Okay, so if we want to find the field at a point P which is at a distance r from the axis of this wire, then what do? The Gaussian surface that we draw is a cylindrical surface. Okay, so we draw a cylindrical surface which passes through the point P and has a radius r and it has a length L. The cylinder that we draw is not of infinite length, it has a finite length L. Of course it's an imaginary cylinder. Okay, now next we see that if you consider the top surface or the bottom surface of the cylinder, then there is no flux attached to it. Why? Because the lines of force are tangential. Okay, the lines of force are tangential to the surface. So if you take E dot A, if you take the dot product of the electric field direction with the direction of the normal to this area, then the angle is 90 degree. So the dot product is 0. So the flux does not have any contribution to the top, from the top and bottom surface. So the only contribution comes from the curved surface. Okay. So once we determine that flux through top and bottom surface is 0, we need to calculate the one from the curved surface. Okay. Okay. So outward flux to the curved surface is E dot ds or E dot n cap ds, and according to Gauss's law, E dot n cap ds is q by epsilon naught. Now we study two cases. Excuse me. In case 1, n cap is r cap because the normal to the curved surface is along the radius and the field is also along the radius. So E dot n cap ds is just E ds. Okay. So we have to find out E integration ds equal to q by epsilon. Now this integration ds is the total curved surface area of the cylinder that we have drawn, the Gaussian surface. So that value is 2 pi rl. So E into 2 pi rl equal to q by epsilon naught. And q, the total charge enclosed by the Gaussian surface, is the charge that is carried by this portion of the line. This is the portion that is enclosed by the cylinder of length L. So the charge carried by this portion is lambda into L, because lambda is the charge per unit length. So q equal to lambda L. So in this equation now we write E into 2 pi rl equal to lambda L by epsilon naught, so that E equal to lambda by 2 pi epsilon naught r. Okay, this provided the point P at which you are trying to find out the field is outside the line. If the wire is thick and the point is inside the wire or the rod, then you can no longer use this method. Then what you will have to do, you will have to write the charge in terms of volume distribution. Okay, so then lambda L will be equal to pi a square L into rho. Pi a square L is the volume of that cylinder of length L, because A is the radius of the wire and we are considering a point inside the wire. Now the wire is thick. Okay, so in this case the new charge that is enclosed within the Gaussian pillbox is q prime, which is equal to pi r square L into rho. And in place of rho, you write this in terms of lambda, lambda by pi a square. Okay. So now you next apply Gauss's law, and this is the new expression. This is when r is less than a. Okay. So we have done these two cases. Now let us move on to the new case, the third case of applying Gauss's law. So I just recapitulated the two cases that we have already elaborately discussed in the last class, just to remind you how Gauss's law is applied. Okay, so you have to first determine the symmetry of the problem, so that you understand what is the kind of Gaussian surface that you are going to so that you can determine what is the kind of Gaussian surface that you are going to draw. Then you have to find out the relation between the direction of the electric field and the normal to that surface, so that you can find out E dot n cap ds, that is the integrand on the left hand side. And then you have to calculate the charge enclosed by this surface. Okay, these are the three steps, after which you directly go to Gauss's law, the equation of Gauss's law, integration E dot n cap ds equal to q by epsilon. Okay. So our third problem is field due to a uniformly charged sphere. Okay. So we will consider a solid sphere which is uniformly charged, and we will find out the electric field for this uniformly charged sphere at a point P, which is at a distance r from the center of the sphere. Okay. So we consider a solid sphere which has a radius capital R, its center is at O, and it has a volume charge distribution rho. Since it is a solid sphere, so now you have to talk in terms of volume charge distribution. So this is one more thing that you need to remember. If it is a linear object which is carrying a charge, you have to consider line charge distribution. If it's a hollow object, say it's a cube, but just the surface, it's a hollow cube or a hollow sphere, then you have to consider surface charge distribution. If it is a solid object, say a solid cylinder or a solid sphere or a solid cube, then you have to consider the volume charge distribution. So since here we have been given a uniformly charged sphere, so we considered the volume charge distribution rho. Okay. So this is our solid sphere. I hope all of you can see that white pearl-like spherical object. To give you the three-dimensional feeling, I have taken this picture from the internet. I can't draw 3D objects on my laptop. So this is a solid sphere which has its center at O and its radius is capital R. And we assume in this particular problem that the sphere is charged with positive charge. The entire sphere is charged with positive charge with a charge distribution rho. So it is a continuous charge distribution rho. Okay. And since the charge is positive, so the lines of force will move out of the sphere in the radial direction. Okay. So we understand from the symmetry of the problem that the lines of force are spherically symmetric. They are coming out radially from the spherical surface, the spherical object. Now what is our problem? We have to determine the electric field E at a point P situated at a distance r from the center of the sphere. Okay. Please follow the steps very carefully so that you know when this kind of a problem comes in your exam, what we usually get in answer scripts is only the mathematics. Okay. Children don't tend to write the things that should be written. If the question is like this. Determine the electric field due to a uniformly charged sphere at a point P situated at a distance r from the center of the sphere. We will only see Gauss's law, integration E dot ds equal to q by epsilon naught. So this, only the mathematics and done. This kind of a question carries at least 4 to 5 marks. Okay, so if you do only the mathematics, then you will get at the most maybe 3 out of 5. Okay, so you need to write down things. This is a physics lesson. This is not a maths lesson. We all know that you know how to do integration. So this is not a maths lesson. Okay, so you need to write these things. The electric field is to be, this is the problem. I have not yet gone to the solution. So the information given is, we have a solid sphere with radius capital R, center O, and volume charge distribution rho. The electric field E we have to evaluate at a point P which is situated at a distance R from the center of the sphere. Now the solution begins. Okay, so we have to find the electric field E at a point P which is at a distance R from the center of the sphere. Now let us first consider that R is greater than capital R. See, in the problem it is nowhere written whether this small r is greater than capital R, equal to capital R, or less than capital R. So if this general statement is given, then you have to consider all the cases. If it is said that the point P is situated outside, then you can just do the problem for a point P situated outside and leave it at that. But if it is not mentioned whether P is outside the sphere or inside the sphere, then you have to consider all the cases. Okay, so this is case 1, where the point P is outside the sphere and small r is greater than the radius of the sphere. Okay, so what do we do next? We draw the Gaussian surface. So here the problem is spherically symmetric. So we draw an imaginary spherical surface of radius r, which is concentric with the charged sphere and passing through the point P. Okay, so this is our Gaussian surface. All right, or pillbox. We can call it a pillbox too. So remember, this is an imaginary surface. This is not there. We draw this to apply Gauss's law. So this is a spherical surface that we draw, which is why I always, if you notice, I always draw the Gaussian surface with a dashed line. I never draw a solid line to indicate the Gaussian surface. The Gaussian surface is always drawn with a dashed line because it is an imaginary surface. Okay, so we draw this surface such that it passes to the point P where we want to find the field, and therefore it has a radius r because it is concentric with our given sphere. So its center also lies at O. So now we have to apply Gauss's law to this surface, which Gauss's law tells us that surface integral E dot n cap ds equal to q by epsilon naught. Okay, now total charge q enclosed by the Gaussian surface is the total charge on this sphere that is given. Okay, so the solid sphere has volume 4/3 pi r cube and its volume charge distribution is rho. So the total charge on the sphere is q equal to 4/3 pi r cube rho, and this charge is entirely falling within the Gaussian surface. So the total charge enclosed by this Gaussian surface is this value, 4/3 pi r cube rho. Okay, again here n cap is along r cap. N cap will be the normal to the Gaussian surface at any point. Now the normal to a spherical surface at any point will be along the radial direction. So n cap is along r cap. So electric field E is ER r cap, so that integration E dot, in the Gauss's equation, integration E dot n cap ds equal to q by epsilon naught, we have here the integrand of the left hand side is E r cap dot r cap ds equal to q by epsilon. So we have E surface integral ds equal to q by epsilon naught, because r cap dot r cap is 1. Okay. So what is the total surface integral of ds? The total area of the Gaussian surface. Remember, here you can't get confused. The total area that will be given by this surface integral is the area of the Gaussian surface, because we are integrating over the Gaussian surface. Okay, so it is not the total surface area of the sphere given, it is the total surface area of the Gaussian surface. Okay, so ds integrate surface integral ds is equal to 4 pi r square is the surface area of the Gaussian sphere. I have mentioned it separately, so there is no room for confusion. When we are trying to find the field at a point outside the sphere, the area given by the surface integral is the area of the Gaussian surface, not the actual sphere. So therefore we have in Gauss's law E into 4 pi r square equal to q by epsilon naught, or E equal to q by 4 pi epsilon naught r square r cap. Okay, I have not yet put the value of q. We can see that E, the electric field at a distance r from the center of the sphere, is equal to q by 4 pi epsilon naught r square r cap. Can you identify this expression? Have you found this expression anywhere before? This expression for electric field? Can you recognize this expression? We have found this expression before. We have found this expression before. Can you tell me where we have got this? Anyone? Do you remember? For a
circular axis.
no, we are doing it for a circular surface. Remember the electric field due to a point charge q at a distance r from it. Okay, I'll show you. Point charge q at a distance r from it. Q by 4 pi epsilon naught r square. Okay, there it was just a point charge. It was not a spherical charge distribution, a volume, a solid sphere. It was just a point charge placed at the point O. But the electric field at a point distance r from the charge was q by 4 pi epsilon naught. Here again we have got the same expression where q is the total charge of the solid sphere. So what we can say here is that from this expression that the field at any point outside the sphere is exactly the same as if all the charge is concentrated at the center of the sphere. When you are trying to calculate the electric field at a point which is outside the sphere, the expression of the electric field shows us that it is as if to an observer who is standing at the point P and looking at the sphere, to that observer, it is as if the entire charge is concentrated at the point O. It's as if a point charge of magnitude Q is placed at the point O, and the field at the point P because of it is this. Okay, so this is a consequence of the spherical symmetry. And this happens only when you are calculating the field outside the sphere. So when you are calculating the field outside the sphere, it seems as if the entire charge is concentrated at the center of the sphere. Okay. But for the charge sphere now, but we know that the actual value of the value of Q is not given. You are given rho, the volume charge distribution, and capital R, the radius of the sphere. So you can't give the answer in terms of Q. That was only to show you this expression is not incorrect. But if you are wanting to solve the problem, you get a solution to the problem, then you can't stop here because you don't know the value of Q. You need to calculate the value of Q. This expression using Gauss's law is to show you that the field is, when you are outside and calculating the field, it seems as if the field is concentrated at the center. But now you have to get the actual result, and for that you have to calculate the value of Q, which is volume of the sphere into rho, the volume charge distribution. So 4/3 pi r cube rho. So E is equal to 1 by 4 pi epsilon naught r squared into 4/3 pi r cube rho. Q by 4 pi epsilon naught r square. This is the magnitude. We are not considering the direction here anymore. We know the direction is along r cap. So simplifying, we get E vector is equal to capital R cube by small r square into rho by 3 epsilon naught r cap. Okay. So rho r cube by 3 epsilon naught is a constant for a given sphere. So it goes as 1 by r square and is directed along r cap. Okay. So this is the field in terms of the volume charge density when you are trying to calculate it at a point outside the sphere. Alright. Now let us consider the case when we are inside the sphere. So R is less than capital R. This is case 2. Okay. So the charge sphere is the same, but the point at which the field is to be determined is now inside the sphere. So this was our charge sphere with capital R as the radius. Case 1, we studied how we find the field at a point outside the sphere. Now suppose we want to calculate the field at a point which is inside the sphere. So R is less than R, and as I told you, if it is not mentioned in the problem whether the point P is outside the sphere or inside the sphere, then you have to give all the cases. Usually it is mentioned in the problem. If you have to mention all the cases, then it is a very long sum, but not very difficult, only different cases. Okay, so now we have a point P which is at a distance r from the center, just that small r is now less than capital R. Okay. The Gaussian surface is an imaginary spherical surface of radius r, still concentric with O and passing through the point P. Everything same, only small r is less than capital R. So this is my new Gaussian surface. Okay. It lies inside, not outside, because r is less than capital R. But having said that, when we apply Gauss's law to this surface, when we apply surface integral E dot n cap ds equal to q by epsilon naught to this new Gaussian surface which is inside the solid sphere, we have to remember that everything else remains same. E is still along the radial direction, n cap is still along the radial direction. So E r cap dot r cap ds, which gives us E integration ds equal to q by epsilon naught. This integration ds is still the surface area of this Gaussian surface, so it will be 4 pi r square. Okay, and but now q, the charge enclosed by our Gaussian surface, is no longer the total charge of the sphere, because the Gaussian surface is now inside the sphere. So all the charges that lie outside the sphere, outside this surface, will not contribute. Have you understood this? Everything else is same, but since now the Gaussian surface lies inside the solid sphere, so Q, the charge enclosed, is only the charge lying within this sphere of radius r. Any charge on the sphere that lies outside the Gaussian sphere does not contribute to this point P, to the field at the point P. So we cannot consider that. Okay. So the charge enclosed is 4/3 pi small r cube rho, not capital R cube rho. It is 4/3 pi small r cube rho. Okay. This much you have to keep in mind, that when the point is inside, we have to consider only that portion of the solid sphere which is enclosed by my Gaussian surface. Any charge that lies outside this is not contributing to the field inside. Okay. So now in the Gauss's law, we write E into 4 pi r square equal to 4/3 q by epsilon naught. So E is 1 by 4 pi r square epsilon naught into 4/3 pi r cube rho. Okay. So see, now the capital R value does not have any role to play in the expression of E. So E is just r rho by 3 epsilon naught. Okay. And in vector, in terms of vector, E is equal to r rho by 3 epsilon naught r cap. Okay. So when small r is less than capital R, that is when we are at a point inside the sphere, the value of the electric field is r rho by 3 epsilon naught. Clear? Next, let's see what happens at the surface. Suppose you are asked to find the electric field just at the surface of the sphere at r equal to capital R. If you use the expression of E for r greater than capital R, which is this r cube by capital R cube by small r square into rho by 3 epsilon naught r cap, and put r equal to capital R, small r equal to capital R, okay, then what do you get? E equal to rho r by 3 epsilon naught r cap. Okay, we just substitute small r by capital R because they are same. When we are at the surface of the sphere, then capital R equal to small r. So using the expression of E for r greater than R, okay, so suppose so we are at a point P and we slowly decrease the value of small r until it becomes equal to capital R. Okay. So we start with the expression of the value of r greater than capital R and decrease it to the value of r equal to capital R, so that in this expression we get the expression of E at the surface as rho r by 3 epsilon naught r cap. On the other hand, if you use the expression of E for r less than r, so you start from a point r which is less than r and then slowly increase small r when it is equal to capital R. So in this expression, when r is less than capital R rho by 3 epsilon naught, if you put small r equal to capital R, you again get E equal to r rho by 3 epsilon naught r. So whichever expression of E you use, whether you use the expression of E for r greater than capital R or you use the expression of E for r less than capital R, when you put small r equal to capital R, you get the same value. Okay, rho r by 3 epsilon naught r cap. So at the surface, the electric field has the magnitude rho capital R by 3 epsilon naught, which is a constant obviously, because for a given sphere capital R is a constant and rho is a constant. Now if you look at these two expressions of E for R greater than capital R and R less than capital R, you see for R greater than capital R, E is proportional to 1 by R square. So E is inversely proportional to R square. So greater the value of R, lesser is the value of E. So the more you move away from the sphere, the value of the electric field, the strength of the electric field weakens, it decreases. On the other hand, for R less than capital R, you see E is proportional to R. So E changes directly as R. The more you move away from the center of the sphere, that is, the more you increase the value of R, the value of the field increases. Can you tell me why that happens? That happens because when you are starting from a point inside the sphere, say you start from R equal to 0, that is right at the center. So there is no charge enclosed, so there is no field. As you start moving from the center, so I'll show you this picture. So as you start moving from the center and increase R, more and more charge is being enclosed. Okay, so the value of E increases until you reach the surface. So when you start increasing R from the center towards the surface, the value of E increases directly as R, because the further you move from the center inside the sphere, the more amount of charge is being enclosed and more amount of charge is contributing to the field. So the value of field increases. Once you are at the surface and you start moving further away from the center, the value of the charge can no longer increase because that is fixed now. There is no charge outside the sphere. So when you are outside the sphere, the contribution is fixed. So the field can no longer increase. But now it decreases with distance because its strength weakens as you move away from the sphere. Okay. So when we are inside the sphere, field is directly proportional to R. When we are outside the sphere, field is inversely proportional to R square. So if you draw a curve, if you are asked to draw a curve showing the relation between electric field and distance from the center of the sphere, okay? So this is my sphere, this dashed line is my sphere of radius R. Okay, so when you start from the center and move towards the surface, the field changes directly as R rho by 3 epsilon naught, R rho by 3 epsilon. At the surface, it has the maximum value, capital R rho by 3 epsilon naught. And then when you start moving outside the surface, now you are outside the surface, it starts decreasing as 1 by R square. Okay. At this point, it has the maximum value R rho by 3 epsilon. Whether you are approaching from inside the sphere or you are approaching from outside the sphere, at R equal to R, the value is the same, the maximum. So this is a very, very important curve. You are often asked to draw it in the examination. You have to remember that this is how the change takes place. There is nothing to learn by rote. You have to understand and learn. When you are inside the sphere, as you move away from the center, more and more charge is being enclosed, contributing to the field. So the value of the field increases, and this is the expression how it increases. It increases linearly with R. So this straight line from R equal to 0 to R equal to capital R. Once you start moving outside the sphere, there is no more charge that can increase the field. The charge becomes constant, that of the given sphere. So now when you move away from the sphere, you will feel the strength to be weakening slowly. How? What is the relation? It is inversely proportional to r square. So as you move away from the sphere, see, this is the sphere, inside it is increasing and outside it is decreasing as 1 by r square. Okay, is this clear to everybody? Do you have any questions regarding this? Okay, if not, then we will move to the next problem. So I have done the problem of the solid charge sphere comprehensively with you. Okay, whatever can be said for this problem, I have said everything, I mentioned everything. So whatever question comes from this part, you should be able to answer. Okay, it will not come as an entire question. The question might ask you to find out the field outside the sphere, or inside the sphere, or at the surface, or it might just ask you to show you this graph, show how the electric field varies as you move from the center of the sphere to a point which is outside the sphere. Then you have to do this page. Okay, say that inside it is proportional to r, outside it is inversely proportional to r square, and at the surface it has the maximum value, so that this is how the variation takes place. All right. Okay, next problem, number 4, is the field due to a uniformly charged spherical shell. So we spoke about a solid sphere. Next problem is to find out the field due to a uniformly charged spherical shell. Okay, so now we consider a charged spherical shell which has inner radius a and outer radius b, and volume charge density is rho. That is the information given. So we are not considering a solid sphere, we are considering a shell. So this is what we are considering, a spherical shell. Okay, again this is a three-dimensional object, but I did not find a three-dimensional figure even on the internet for a shell. So this is a cross section. Okay, inner radius a, outer radius b, and for the solid portion the charge density is rho. Okay, it is taken from this website. Now the electric field again is to be found out at a point P situated at a distance r from the center of the sphere. Now this problem I will not do entirely. Part of it will be given to you as homework, because we have done the solid sphere with great detail. So we have to again consider three cases. Case 1 is r less than a. So the point P at which we want to evaluate the field is inside the shell, less than a. So it is inside. Okay. So point P at a distance r from the center is less than a. So this is the Gaussian surface. Okay. We have to apply Gauss's law. Surface integral E dot n cap ds equal to q by epsilon naught to this surface. But if you look here, then the charge enclosed by this surface is 0, because it's a hollow shell. This white portion is hollow, there's nothing here. The charge is on the solid shell portion. Inside the shell there is nothing, it's hollow, empty. So there is no charge enclosed. So Q is 0. So when you are trying to find out the electric field inside this shell, then you can see from Gauss's law, applying Gauss's law, since enclosed charge is 0, therefore in E into 4 pi r square, the right hand side you have to put Q equal to 0, so E equal to 0. So when you are inside the shell, within the shell, at a point inside the hollow region, there is no electric field. Okay. Next case is when R is in between A and B. A less than R, less than B. So P is somewhere here. Point P at distance R from the center, between A and B, between the inner shell and the outer shell. Okay, so it is somewhere within here. So now we draw the Gaussian surface, and it is something like this, lying within that shell region. Okay, so what do you have to do? So if you look at the Gaussian, see, the contribution to the electric field will be from the charge enclosed. The portion of the shell that lies outside this dotted line will not contribute. So you have to calculate the charge that is lying within the Gaussian. Okay, so if you apply Gauss's law, then now the charge enclosed is this 4/3 pi r cube minus a cube. The charge lying within the volume, that is between the inner shell and the imaginary Gaussian surface, multiplied by rho. Okay, and of course surface integral ds is 4 pi r square. So I want you to put these values in Gauss's law and find out the expression for electric field. Everything has been done. I have told you what the value of integral ds is. I have told you what q enclosed is. So you just have to put it in Gauss's law and find out E. Okay. And case 3 is similar. R is greater than B. That is, the point P is outside the shell, somewhere outside the shell. Okay. So this is my Gaussian surface. And as you can see, now we can consider the entire shell to be contributing to the flux. Okay. So the charge enclosed will be the total charge of the shell that has been given. So now Q enclosed in case 3 is 4/3 pi b cube minus a cube. That is volume of this solid shell multiplied by the volume charge distribution. Integration ds is again 4 pi r square. It is always the surface of the Gaussian surface, total surface area of the Gaussian surface. So once again I want you to put these values in Gauss's law and find out the value of the electric field. So you have two homework today, two small little work to be done. One is find out electric field when R is between A and B for the shell, and 2 is find out the electric field when R is greater than B, that is outside the shell in case of a spherical shell. Okay. Okay. Finally, this is the last portion of the spherical symmetry problem. Field due to a uniformly charged thin spherical shell. We want to find out the field due to a uniformly charged thin spherical shell. So we saw what the field due to a solid sphere is. We saw what the field is due to a thick spherical shell, and we studied all the possible cases when the point P where the field is to be determined is outside the sphere, inside the sphere, at the surface, outside the shell, inside the shell, within the shell. Now we will consider the simplest case actually, when the spherical shell is thin, that is we don't have to consider the thickness. Okay, the thickness of the shell is negligible and the radius of the hollow sphere is r. So it's the same spherical object, but now the inside is hollow. Understood? There is nothing inside, it's just a hollow sphere. It's like a football. Inside there is hollow, nothing inside, it's just the surface. Okay, you understand? It's not like a watermelon, no pulp inside. It's like a football, it's hollow inside. Okay, so since it is hollow, now we can no longer consider the volume charge distribution. We have to consider the surface charge distribution. It's hollow, there's no volume, it's empty inside. So no, volume charge distribution doesn't make sense. The charge is mirrored on the surface. So we have to consider the surface charge distribution, that is sigma. Once again, electric field to be evaluated at the point P situated at a distance r from the center of the sphere. So case 1, r is less than capital R, somewhere inside the spherical shell, thin spherical shell. So we draw a Gaussian passing through the point P with radius r. apply Gauss's law, but Q is 0 because as I told you right now that it is a hollow sphere, so there's nothing inside. So there is no enclosed charge. Q is 0. So in this case, E is 0. So just like the solid spherical shell, when you are talking about a thin spherical shell, then if you are considering finding out the field inside the shell in the empty region, there is no field over there, no contribution of the charges at a point which is inside the shell. Case 2 is R is greater than capital R. You are at a point outside the shell. Okay, so point P is outside the shell at a distance R. There you want to find out the field. So once again you draw the Gaussian surface passing through the point P with radius R. Apply Gauss's law. Now what is the enclosed charge? By this, the total charge that is there on this spherical surface. Okay, so Q is 4 pi capital R square, surface area of this sphere multiplied by sigma, surface charge integration, surface charge distribution. Okay, so this is the total enclosed charge. So you have to find out in each case. You can see that the enclosed charge becomes different. In this particular case, since it's a hollow sphere, the surface charge, the total charge enclosed becomes the surface charge distribution multiplied by the surface area of the hollow sphere. So it is 4 pi capital R square into sigma. So, and of course integration ds is 4 pi small r squared because that is the surface of the Gaussian that you have drawn. So E into 4 pi r square equal to 1 by epsilon naught Q on in the numerator. So 4 pi capital R square into sigma. So the value of E is 1 by epsilon naught capital R square by small r square into sigma multiplied by R. So capital R is given, sigma is given. If you are asked to find out the field at a distance small r from the center, then you just use this formula and find out. Okay, so that completes the spherical charge distribution. Now there are two more applications left. It's 8 p.m. I started the class I think about 5-6 minutes late. So should I finish all the applications today? Will it be too much for you? Do you want me to continue with the other two applications too, or do you want me to do them in the next class? I want your suggestion. I don't want to overload you. I am okay with
Ma'am,
continue for an yes.
how much is left? One or
Two two more applications. One is this field due to a uniformly charged plane. Yes. So this
no.
and
Can,
capacitor. You tell me. It's totally up to you. I don't want to impose it on you because we have time. We will finish the syllabus. Don't worry. Exam will not be before August, so we still have half of this month and July left, so we will finish the syllabus. So but if you are okay with it, then I can do these two applications too. But if you think it is becoming too heavy, then I'll stop at this. You tell me. What do you want? Tell me. Please, someone unmute and tell me. Yes, please, someone tell me.
ma'am, continue.